Hello, everyone. Um, in this session, we have presenters from 4 countries: Australia, Italy, USA, India. So, good morning, good afternoon, and good evening. Welcome to the technical session 2C of World Conference on Smart Trends and System Security Sustainability, World S4 2020. Due to COVID-19, we all are going through a new normal phase. And the team of World S4 wishes you a safe and healthy time for you and your well-wishers. We are constantly trying to overcome the challenges that research community is facing at different level. We at Global Knowledge Research Foundation are fully committed to contribute and enhance the digital experience in research activities. Once again, we all would like to congratulate you for your research work and to be a part of the success story in fourth version of this conference. Further, I would like to welcome our session chair, Dr. Vijay Singh Rathore. He is professor at the IIS University with overall total 18 plus years of teaching experience. He has more than 50 publications to his credit. His area of interest includes cloud computing, IoT, big data, internet security, and machine learning. So, Dr. Vijay Singh Rathore, we welcome you.
A very good evening to all of you.
Yeah, thank you for joining us as a session chair.
Thank
So,
you so much.
so now we move ahead with our technical session. So first, I would like to invite Mr. Hudan Studiawan. Uh, yes, Hudan, I'm just giving you rights to start your presentation, and I'm unmuting you. So he will present a paper on performance evaluation of anomaly detection in imbalance system log data. Yes, Hudan,
Thank you.
welcome.
Uh, yeah. Can I share my screen?
Yes, yes, just a moment. Yes, now you can share.
Okay. Can you see my screen?
Yes, we can.
Okay. Thank you. Okay. I would like to present my research paper entitled Performance Evaluation of Anomaly Detection in Imbalance System Log Data. My name is Hudan Studiawan and I'm a PhD student in Murdoch University, Australia, and Firdaus Sohil is my supervisor.
Sorry, Hudan, but can you keep your mic a little bit closer? Actually, your voice is very low.
Oh, okay.
Or you can speak, a little bit louder.
Okay.
Yes,
Is it
there is a
clear
lot
now?
of disturbance is there.
Is it clear now?
No, disturbance is there.
There is some echo, I think.
Yes, echo or some background voice is there.
Oh, okay.
Now it's okay.
Yes, now it is perfect. Perfect.
Oh, okay. Okay. So,
A little bit louder. Sorry,
yeah.
louder. Thank you.
I would like to discuss the problem about anomaly detection and then anomaly detection and class balancing that I discussed in this paper, and then the data set used in this research, and then experimental results, and finally conclusion and future. So the current methods for anomaly detection use machine learning approaches. Uh, However, most of these methods do not consider the imbalance logs data, which means uh, anomaly data is much small number compared to the normal data. So this leads to this suboptimal performance when detecting anomalies in system log. So this is the framework we discussed in this paper. So there are two parts: training step and then testing or deployment phase. So we have system log files, and then we parse these log files we extract features, and then we do class balancing, and we and then it produces a model file that can be implemented in testing step. And then for deep learning, it's a recent learning techniques. So we only use the step that in blue box, parsing, word embedding, and then this one and this one. In testing, we will need to pre-process the log files and then detect anomalies based on the results from the training. And then we will get the anomaly detection results. In this work, we use 5 machine learning methods to perform anomaly detection. The first one is decision tree, and then logistic regression, and then support vector machine. The first three is traditional machine learning methods, and then we use more recent deep learning techniques. It's a long short-term memory and convolutional neural networks. And then we also consider the class balancing techniques. Basically, there are two common types of class balancing. It's oversampling and undersampling. We use 4 techniques for oversampling. It's random oversampling, and then synthetic minority oversampling technique, and then adaptive synthetic, and then SVM combined with smooth. And then for undersampling, we use random undersampling, and then Tomac links, near miss method, and instance hardness. In this work, we use 3 data sets for system log data. These 3 data sets contain anomalies such as brute force attack or illegal access to a computer or a server. As we can see here, that the number of normal data and anomaly data is not balanced. So that's, I mean, it's imbalance. Efficiency is very small number compared to the normal one. So that's why we evaluate class balancing methods in this work. So based on the experiment results, we can see in this table that the deep learning methods such as CNN, it can achieve best performance, for example, in this area, and this in for another dataset, it also can provide good performance compared to the traditional machine learning methods. So this is key findings in this work. The deep learning models, we use LSTM and CNN in this research, provide the best detection compared to all of the methods. And then unsupervised techniques. So actually we also evaluate two unsupervised methods, is isolation forest and principal component analysis here. Naturally unsupervised techniques show poorer performances compared to the supervised methods. And for the class balancing methods, we found that the adenosine and random effort sampling provides the best detection of anomalies. So this is the conclusion, and this research evaluates popular machine learning methods to detect anomalies in imbalanced system log data. And then we also apply various oversampling and undersampling techniques to address the class balancing issue. Based on our experiments, we recommend sampling methods for oversampling is adhesion and random oversampling. And for undersampling, the Tomac links is also quite good to address the imbalance data of system log. For future, we plan to evaluate more machine learning methods and class balancing methods. Thank you.
So, have you compared your results with the existing outcomes of other researchers, the recent researchers?
Yeah, so we
You have mentioned two, three techniques, I think.
I'm sorry.
You have mentioned two, three techniques, different. DT, LR, SVM, ECA.
Yeah.
So,
we
which is the closest? Which is the closest one with your results?
So actually, in this work, we compare the various methods, and the best methods is shown by deep learning methods such as CNN. It's shown in the bold indicates by the bold value in the table.
Okay, in your own observation, what are the limitations so far in your work, which you would like to improve?
Yeah, so we in this research, due to the limitation of space and space of the paper, we actually plan to train more system log data, because in this research we only um, train on three data sets. So we plan to add more data sets.
Okay, fine. All the best for that. Thank you so
Okay.
much.
Thank you.
Samihir.
Yes, thank you, Dan.
Thank you.
Thank you.
Yeah. So now we move ahead with our next presentation. So next presentation will be given by Libero Negro.
Microphone.
Yes,
Okay.
yes. Hi, how are you? After
Oh,
a
very
long
good.
time.
I remember you from the last year.
Uh,
Last February.
yes, last of February. This time
Yes.
online, but might be next time again in physical in
New
London.
experience for all of us.
Yes.
Yes.
Yes, so please.
I would share my screen.
Yes, sure.
I try. Please tell me if all is okay. My voice, my video.
You can
Yes,
see.
okay, good.
Can I start?
Yes, please.
Yes, please.
Thank you. This is a work which is devoted to software development for supporting cyber physical systems, which today are ubiquitous in many application domains like healthcare, automotive, smart environment, etc. And in particular, we talk about our approach with this field, which is challenging, and our approach, which is based on, sorry that I make a full screen in my presentation, and I'm mentioning our approach, which is called the theatre. Theatre is an actor system which follows some international efforts today, which are in progress, trying to model and then implement cyber physical system. And here I would recall the effort of the Ptolemy community at Berkeley University and the lingua franca approach, which has stressed the importance of using a deterministic approach. And we do in this research try to develop a deterministic version of our theater actor system so as to support in an acceptable way CPS. Now, just to recall, but also this morning in the presentation of Professor Ince, there was some note about the CPS. Challenging of this system is that it derives from the part that they consist of three parts: a cyber part, which is the software, the network, and the physical part. And the two parts, cyber and physical, have a different timing model. And so the challenging in this system is try to reconcile the two timing model and to cope with heterogeneity and the necessity of a determinism. A determinism means that if we have a deterministic system, to a given input, to the same input, we must have the same output. Now, in the actor system traditionally depend on asynchronous message passing and non-determinism. Instead, in our approach, which is based on theatre, we have customized our approach to make it deterministic. Now, in brief, because time does not allow me to go into much detail, technical detail, in our approach, which is distributed, we have various nodes in which each node hosts a subsystem of with respect, for example, to Gulag actors. In other terms, we have a reflective control layer which controls the message delivery. So we buffer messages and apply a strategy of delivery. And exactly upon this feature, we have achieved it, we have moved, we have worked to get a deterministic theatre. Here, I would only mention the fact that when we model a cyber-physical system, we need the normal actor, but also we need some interface actor, which interfaces the external environment. And these actors are fundamental to provide external actions for the software. And the linkage among the two kinds of actors are messages. When a message, a mode actor sends to an accessor actor, in that moment, we hear about the external environment. Okay, now, what about the determinism? In which consists our determinism? We have a model of an actor model in which messages are first of all time-stamped. Each message carries the time tag when it must be delivered. But besides these timestamps, obviously, we first deliver message according to the timestamps, obviously. But the situation happens that we have also messages which are simultaneous. And when we have simultaneous messages, whereas the classical actor system says non-determinism of the delivery, instead we have introduced a partial order which forces a given delivery order. In particular, we introduce to each actor a unique priority, ID, and also to message a unique priority, ID, so that when messages are directed to the same actor, we use the message priority. And when simultaneous messages are directed to different actors, we use the actor priority. So, in other terms, we pretend to control the delivery order according to these rules. And we have defined different tools to prove properties of a CPS model according to this ordered delivery of messages. We have a simulator in Java, but also we have a reduction in the open model checker, which allows us to make some exhaustive analysis. Now, to give you an idea, we have applied our methodology to a simple, apparently simple example, which is a train door controller. In this example, we have a train door, which obviously can be opened and closed, locked and unlocked. The door can be locked only when it is closed. The train can be moving, obviously, provided the door is locked. And if it is locked, it is necessarily closed. When the train stops moving, obviously the door must be first unlocked, then opened. Now, this apparently simple system is driven by the environment, because we have the action which originate in the environment, which must dealt with in the controller. And we also have assumed that the existence of an open button for passengers, which can be acted in order to ask possibly for the door to be opened and so to stop the train. But the open button actually can be heard only in the case the door is not yet locked. It can be closed but not yet locked. If it is locked, obviously it cannot be opened and the train cannot stop. So we have modeled this system using in this case, four actors, main, which is configuration, train and door, which are interface actors, and the controller, which is a real-time controller. What is interesting is that we have precise times in which the various events can occur. And to give you some idea about our programming style in Java, here is, for example, the train actor modeled in Java. We have a safety property to verify in the sense that never can occur that the train is moving and the door is opening, obviously. And this must be checked before we build the system, the software system, which is in control of the physical system. Now, in order to make exhaustive model checking of this system, we have modeled the system, the train door, also in Opal. And this, in this slide, you can see the priority, which is the unique identifiers which we associated to the actors, and also to the message names. Then we have modeled each entity, the train, the door, the controller, the main, which configures and puts the system into operation. What is very interesting in this modeling, without entering in so much detail, is the so-called scheduler. In our previous work, when we have done some similar work, we modeled in Opal both messages, delays, etc., as a separate template processes, each one with its own timing. But in order to have determinism, in this case, we originally introduced the concept of a scheduler. The scheduler is in charge of capturing all the scheduling of messages and of applying the deterministic message delivery order. So we have verified the system, and the system effectively behaves as the modeler expects. For example, when the train is moving, we are asking, for example, in the second query, if the door can be opened and the controller, which says the train is moving, this property is not satisfied. Effectively, in no case we can have that the train is moving and we violate the safety properties. And so the other property, for example, the last two mentioned, what happens if the controller receives an external open, the button which the passenger can press, and the controller, here is a query which is based on the leads to operator. In the sense, the meaning is this: provided that we received an external open, it always follows that the door is opened and the train is stopped. This property is not satisfied because the problem is that the external open can arise when the door is locked and then it no longer can be stopped, and etc. The key point of this model checking is that the correctness of a system like this strictly depends on the time assumption. And this is the same viewpoint of our colleague at the Ptolemy community, and also for our system, because this is an intrinsic feature. On the physical system, we have a Newtonian time. On the cyber system, we have a discrete time. We must reconciliate. We must, in a way, to put in relationship this kind of timing. And so all depends on this relationship. In this moment, we are working into putting into real-time operation the concept which already we have analyzed through, for example, through Opal. So in this moment, our effort is geared to develop in Java a real-time controller which applies the same precedence constraint on the delivery order. Okay, thank you for your attention. Sorry if I have not observed exactly the time, sorry.
So it's a very nice work, I think, presented by you. Am I audible?
Yes,
Am I audible?
please.
Am I audible?
Yes, sir, you can. Please go ahead.
Okay, okay, okay. Sir, in case of the extreme conditions like the sensors are not working or there is electricity off or some accident happened with the train, have you taken in the consideration all these things also?
You are asking about how to cope with
Some
some
extreme conditions.
some exceptional conditions.
Yeah, exceptional conditions like sensors are not working properly or there is some accident or some
Obviously,
electricity goes off and something like that.
yeah, obviously, to put a system, a complete model of the system must also involve the recovery action, which in general we must uh,
Mhm.
execute to cope with this exceptional event. But what this situation must be explicitly modeled by
Okay.
the modeler, and then we can accept that something completely unacceptable happens during the runtime, because in this case the model was partial.
Mm-hmm. Fine, sir.
So
Thank you.
some recovery must be introduced explicitly, obviously.
Mhm. Thank you,
Okay.
sir. Thank you so much.
Thank you for your
Uh,
question.
yeah, thank you. If any other person has any question with Libero, please write into the chat box. If you need, if you want, you can exchange email addresses in that. Um, and there is this is a virtual conference, so might be we can't give applause to the presenter, but at least there is the option reaction in the bottom of our Zoom app. So yes, we can give at least this appreciation to every presenter. Thank you, thank you. Yes, thank you. So we move ahead with our next presentation. So it will be by Srikant, uh, and he will present a paper on weight in motion sensor based electronic toll collection system. Yes, Srikant, you can share your presentation. Yes.
Hello everyone.
Yeah.
Hello.
Yeah, I'll try to share my screen. 1 second. Yes. Yeah. So I am going to present the paper on weight in motion based sensor based electronic toll collection system. So I am Srikant and my co-author was Purnima, and we both were affiliated to the BMS College of Engineering. I pursued my bachelor's in electronics and communication there. So I'll proceed to the presentation. So the flow of the presentation will be like this. First, I'll talk about the introduction, and the second one, I'll talk about the current methods of toll collection, and then we'll discuss a few limitations of the methods of the toll collection presently in India, and then we'll talk about the objectives of the proposed model that we are proposing, and we'll try to explain the different components of the proposed model. Then we'll go to the simulation and effects of the proposed model. Then we'll conclude it. So currently, the road networks in India, it is one of the largest road networks in the world. It spans of about 5.89 million kilometers. It is one of the largest road networks in all over the world, and it has been consistently increasing since 2014. As we can see from this graph here, this graph was a study made by the Indian Brand Equity Foundation on road and infrastructure analysis. It says that the highway construction in India has been steadily increasing from 2014 through 2020. So this road network caters to about 64.5% of the goods transportation. This goods transportation relates to the transportation and logistic companies, which which try to move goods from one part of the country to another. And this road network also caters to 90% of the India's passenger transportation, which people use to commute. And this increase in the road network, it requires increased maintenance costs. So to achieve, to maintain these roads, they will need to collect toll taxes or toll prices at the toll plazas. So the existing toll collection method under the by the National Highway Authority of India is the National Electronic Toll Collection Program, which was recently launched in 2014. It uses a FASTag system called as FASTag system, which is based on the radio frequency identification tags. So what happens in this is every vehicle is issued a RFID tag, and this tag is used to uniquely identify the vehicle at the toll plaza. And then the price of the toll is based upon the vehicle class of the detected vehicle based on the RFID. So a few advantages of this system is that it will promote cashless payments. So in the back end of this system, the customer has linked his bank account to the FASTag system. So whenever the vehicle is passing through the toll, automatically the RFID is detected and a certain amount is deducted from the bank account of the customer. So this promotes cashless payments, and further it reduces the congestion and saves time and fuel. So this method of toll collection does not enforce the requirement of a manual toll operator because it is automated. This will keep a steady flow of traffic, and thus it reduces the congestion and saves time, which occurs at the toll plazas usually. And interoperability across India. So the point here is this one RFID tag can be used to commute all over India. So across any state or anything within the country, one RFID tag can be used. So now a few limitations of this FASTag collection system is that the toll pricing is based on the classes of vehicles. So in India, the RTO has divided the vehicles into different classes, say cars, minibus, low weight commercial vehicles or trucks. So the toll pricing is based on the vehicle class, and this method of toll collection does not account for the damage caused by the weight of the vehicle on road. So a study which was made by the American Society of Civil Engineers says that the damage caused by an overloaded vehicle is at least 50% greater than the vehicles operating within the permissible limits. So this method of toll pricing collection based on class does not account for the weight of the vehicle. Say a fully loaded truck and an empty loaded truck has different significantly difference in weight. So thus that difference in weight is not accommodated in the current toll collection system. So another shortcoming of our existing toll collection system is that there is no check to ensure that the overloaded vehicles are not allowed to travel on the highways. So as we can see in this picture, this is one of an overloaded truck, and there are a few threats that these overloaded vehicles pose to the other commuters and to the damage to the road. So one of it is the improperly secured loads. As you can see, the load here is improperly secured. So this is probably fatal to any other commuter who's traveling on the highway. And the second one is due to excessive load or overloaded vehicles, we can see that the tire on the right side of the axle is having more strain than the left side. So this might cause the tire to blow out, and this might lead to fatal accidents or even worse situations on the highways. So our objective to propose a model is to cater to some of the limitations that we previously discussed. So first thing is we will try to propose a model which calculates the toll prices based on the weights of the vehicle at the time of toll collection. And the second one is this model will try to prevent the commute of overloaded vehicles on the highway. And the third one is that we will try to track unregistered and uninsured vehicles on the highways in India, especially. So what happens is in India, there is no regular checks on vehicles that ensures that the only registered or insured vehicles travel on road. So if there is any place that these checks have to be performed, it is probably at the toll plaza. So our model also takes care of that. So now this is the proposed methodology or the block diagram of the system that we are proposing. So the FASTag system that I discussed is in this block. So This is a separate block, and the model that we are proposing is on the left hand side. So the point here is that our whatever model that we are integrated with the existing FASTag systems. So I'll try to briefly explain what is happening here. First of all, the vehicle will come near, when the vehicle arrives near the toll plaza. There will be a WIM sensor system. So WIM stands for weigh in motion sensor. Near the toll plaza, and the vehicle passes over it. And this system, the output of this system, the toll decision pricing and verification systems. So we'll come back to that later. Now, the second part of the system is that the number plate recognition system. So what happens here is we will use a camera to capture the image of the vehicle, and we will try to extract the number plate and try to recognize the registration number of the vehicle. I'll explain in detail later about the algorithm, but the output of this system would be a string which would represent the registration of the vehicle number. So this registration number of the vehicle is used to query from the vehicle's database, which contains the details, registration details, insurance details, and RC status, and the gross vehicle weight ratios, and the model, the owner details, everything is present in the vehicle's database. So those details are obtained, and those are also passed to the toll decision pricing and verification systems. So what happens here is the weight from the WM sensor system and the maximum allowed weight for the vehicle is compared. So if the weight is greater than the maximum allowed weight, then the vehicle is overloaded. So in such cases, we should not allow the vehicle to pass through. And similarly, if the insurance or the registration of the vehicle is expired, or if it is not valid, such vehicles are also should not be allowed to commute. So that also is taken care in the decision and the pricing systems. And finally, the output of this system is given to the RFID FASTag systems. So that would be the either it would be the toll decision that would be either to allow the vehicle or not, or if the vehicle is allowed, then the toll price is calculated based on the weight, and it is passed on as input to the FASTag system. So yeah, so first talking about the WIM sensor system. So
Yes, sorry, Srikant, but can you try to complete in 2 to 3 minutes? Thank you.
Yeah, okay.
Very interesting, but we have limited time.
Okay.
Yeah.
Yeah. Okay, I have 3 minutes, right?
Yeah, 2 to 3
It's
maximum.
Like a story.
Okay.
Yeah.
Okay. Sorry. Okay. So this WIM sensor system, it will have a quartz crystal, which is very sensitive to strain caused by the weight of the vehicle. As we can see in this picture, the wheel of the vehicle will pass over the system, and it will calculate the weight of the vehicle. So the difference in calibration will result we can use to calculate the gross vehicle weight at the time of toll collection. And this dynamic weight is used to calculate the toll price in later stages. And the second part would be the installation of the system. This picture tells us how these sensors can be installed near the toll plaza. So these are embedded inside the road pavement, and few inductive loops. These inductive loops are used to detect the entry and exit of a particular vehicle. And then the second part is the number plate recognition system. So like I said, we use a camera to capture the image of the vehicle, and then we apply image processing techniques such as grayscale, filter the noises and edge detection. And then finally, we apply the counter approximation to extract the region of number plate from this image, from the car image. So, and we use this image to create a mask and then apply it to the original image to obtain the number plate image.
Excuse me, Srikant.
Yeah.
When we talk about FASTags, I think in the FASTag chip there is already number system and registration number system. Everything is embedded. So why there is a need to capture this number plate again?
No,
yeah, in FASTag it's already there. Number plate and bank account, everything is attached there in RFID.
This system, there are more than one use to find out the NEC. The point is there are already CCTVs which are equipped in the toll plazas. So these systems can be used to detect the theft vehicles or any vehicles which are illegally traveling.
We are talking about FASTag systems, and there is no need of explicitly putting this recognition system. Because FASTag itself embeds everything like registration number, insurance details, bank account details, credit card details. Everything is there in the FASTag.
Yes.
So I think it will like increase the complexity of the system. No?
Yes. Yes.
So you
But
can think about again. You can think about it.
yes. I'll think
Yeah.
about this. And then we can extract the number plate using, we can extract the registration number from this number plate.
Yeah, it was earlier. It was there. I think this system was there before the FASTag came.
Yeah.
But after the FASTag introduction, I think there is no need of this registration buggy.
Okay.
You can just review this.
Yeah. Okay. And then the India RTO provides a database which is called as Vahan database, which
Yes.
provides the database for registered vehicles. It has about 286 million vehicles information, but this is not available.
One more advice I would like to tell you.
Yeah.
Like, how can we calculate that the vehicle is insured or not? Because insurance details are not dynamically updated. So how do you get that?
No, in this database, the vehicle informations are dynamically updated. So
This Vahan, I think this Vahan doesn't give you the insurance information.
no,
Vahan
I have
gives
an
you only
example.
RTO details.
See here, see the example of a Vahan database. We get the insurance details, insurance up to
It gives?
this.
Okay,
Yeah.
good.
So the registration validity and the insurance validity is both obtained from this database. So we can extract. So we can use that number plate, and we can extract these details from this database. And
Okay.
I think
finally,
in Vahan 1 year back it was not there. I'm not sure if it is implemented in last 6 months or so. Because before one year, I think there was no insurance details with Vahan when we
okay,
get this.
okay.
Okay, that's fine.
Okay.
Nice.
Okay. Yes, Srikanth, please conclude.
Yeah. So these details are then used to calculate the weight of the vehicle and check if the vehicle is overloaded. And then it will also perform checks for registration, the 3-level checks saying the registration details, vehicle insurance, and finally the toll decision whether or not to be allowed is calculated from all these data points. And if the decision is not allowed, then the toll officials will be alerted and further actions will be taken. If it is allowed, the pricing will be based on the dynamic weight of the vehicle. So this deduction will link to FASTag, and it will happen in the backend. And finally, this is a simulation of the process where the toll deduction takes place. This is the sequence of whichever I explained. The sequence happens in this order. And for one scenario where the overloaded vehicles, we do not allow, say it'll tell maximum allowed weight is this, and we do not allow the.
Okay, what tool you use for this simulation purpose?
We used Python, VS Code, Visual Studio.
Which tool?
Visual Studio, Python.
Visual Studio Python. Okay, great.
Python,
fine.
yes. And yeah, I'll conclude.
I think now you can conclude this because we have very limited time.
Yeah, sure.
Already 5-6 minutes extra we have.
Fine. So when you calculate, one last point that I want to tell is when we actually calculate the price based on weight, there's a difference in prices that we observe here in the last column. The difference in prices is for a fully loaded and an empty loaded car. So any transportation or anybody who's commuting will be able to save the amount of money in the last column that I'm showing. So he will be able to save that much money. So finally concluding, this is beneficial for the highway authorities because they will be able to track which vehicles are moving and which vehicles have been thefted or which vehicles are insured, like I said. And this is beneficial for transportation logistics because they will be able to save money in the toll prices, because an empty load truck will pay less than the fully loaded truck. And overloaded vehicles are not allowed in the system, and insurance registration verification will take place. And this is easily integratable with the FASTag system. So, and this operates in the scope of autonomous systems. So this will not change anything. It will save fuel. It will reduce congestion at the toll plazas. Thank you. That is the overall.
Okay. Okay, Srikanth, thank you.
Very nice.
I
Very
think,
interesting topic.
yeah, yes. If anyone has any questions, you can write into the chat. So we move ahead with our next presentation. It will be by Ginny Goyal, and she will present a paper on analysis of Parkinson's disease diagnosis using a combination of genetic algorithm and recursive feature elimination. Yes, Ginny, you can say your presentation. And please stick to the timeline of around 8 minutes. It will be good. Thank you.
Is my screen visible?
Yes, it's
visible.
Yes, visible.
And my voice is properly audible?
Everything
Yes.
is good.
Thank you. Hi everyone, my name is Jeannie Goyal. I'm from Peck University, Chandigarh, India. Good evening everyone. The topic of my presentation is analysis of the Parkinson disease diagnosis using a combination of a genetic algorithm and recursive feature elimination. Parkinson disease is a neurological disease which occurs due to the loss of dopamine producing cells in the body. These cells are responsible for maintaining a balance between the body and the various parts of the brain and the various parts of the body. When these cells starts to die, there is a problem of brain and body coordination, and different symptoms starts to appear. Broadly, the symptoms can be classified into motor symptoms and non-motor symptoms. Initially, there may or may not be any symptoms visible at all, and there need not to be present that all symptoms are present. Observing 2 or more symptoms are essential to diagnose the Parkinson disease. Motor symptoms include tremor, rigidity, bradykinesia. Bradykinesia refers to the slow movement, facial masking, low brain rate, postural instability, that is the person is having a problem to stand upright or to maintain a steady posture. They have the inability to prevent falls. There is a problem of walking or gait difficulties. There is a problem of dystonia, that is they are having an involuntary and repetitive movements on which they have no control. Next is voice distortion. Voice becomes very light and less audible. As we speak, we give expressions through our voice, but they are not able to give that expressions. And the non-motor symptoms include sleep problems, depression, anxiety, pain, hallucinations, fatigue, and there are other non-motor symptoms. Now, what are the causes of the exact causes of the Parkinson disease are not known. The major things that can affect our genes. For example, if a person has a hereditary line of having a Parkinson disease, then there are more chances of developing a Parkinson disease. Next are environmental factors, like if the person is more prone to pesticides, chemicals or weedicides, they have more chances of developing a Parkinson disease problem. Then there is a presence of Lewy bodies. What are these? These are the lumps of the protein that are formed in our body due to which dopamine producing cells are reduced. Now, this is the literature survey related to our work, which includes the feature selection techniques that has been initially used. First involves standard feature selection technique like autocorrelation feature evaluators, gain ratio, information gain, SVM evaluator. Then there is improved Gray-Wolf optimization. Multi-layer perceptron has also been used as a feature selection technique. How they have used it? They have used the weight of the multi-layer perceptron as a feature to select the most prominent ones. The ones that are having high weight are selected for feature selection. Next is L1 non-support vector machine, principal component analysis, genetic algorithm, particle swarm optimization. Of all the symptoms that are present in the Parkinson disease, 90% of the patient are found to have a voice disorder. So we have chosen voice as a symptom to detect the Parkinson disease. We have taken a UCI machine learning repository which consists of 31 subjects and 195 instances. 22 features are there and 6 focal phonations are taken from the patients. Head-mounted microphone is used. Normally we can use a smartphone also. So it is very easy to collect data. Sampling rate is 44.1 kilohertz. Now this is the proposed framework that we have used. What we have done is we have taken 2 different feature selection techniques and applied a 2-stage feature selection technique to solve the problems that were present in the literature. These problems are discussed ahead. First of all, I would like to share what is the framework. First of all, we have taken a Parkinson data set and normalized the data set so that all the features are given the equal value. Next, we have simultaneously given the data set to the genetic algorithm and SVM RFE. Genetic algorithm, initially we have initialized the number of generations, number of population, probability of mutation, crossover probability, and created a random population of size n. Next, we have selected at random k strings. We have taken k here as 3. Out of the 3, we pick the best one and select 2 parents. From that 2 parents are crossover and 2 children are created and mutation is done, and finally 2 mutated children are there. Now this changes the population, and now with the new population, our accuracy of the model is checked using SVM with the 5-fold cross validation technique. Now from the mutated children, if there is the accuracy is improved, that means our population, the new population which is created is better one than the previous one. So we will select the new population, or otherwise we'll start the process again. Next we will check if the population size, for example, we have taken population size of 80. So if the population size is met, then we will check the number of generations that we are required. Otherwise, we'll perform the same method again and again to get the final children with the best results. So with this, we have selected X features. Similarly, simultaneously, parallelly, SVM RFE is given and Y features are selected. Two-stage feature selection is technique, and the common features are extracted, and SVM is used to average the results. Now these are the feature selection, the features which are selected after the two-stage feature selection technique. Genetic algorithm is able to select 11 features after 100 generations and population size of 180. Similarly, SVM RFE is able to select 12 features, and after the common 9 features are selected. Why we have chosen genetic algorithm and SVM RFE only? Because the genetic algorithm is a nature-inspired algorithm which has a benefit of finding the global optimum. That is, it can find the features which are globally optimum and give the better results. Similarly, SVM RFE is a feature elimination techniques which eliminate features one by one and retaining only those features which are assumed to be most important.
Jenny, excuse me. You have last 2 minutes to conclude.
Yes. For these are the experimental results. Now, why we have chosen to work on the feature selection technique? As we can see that initially the specificity of the model is 52%. Specificity refers to the data points which are actually correct and detected correctly. For example, if the person is healthy. Now this is very less, but the accuracy is good. So accuracy cannot be only considered as a measure. So to increase the specificity as well, as we have taken a two-stage feature selection technique, and we have able to increase the accuracy to about 70%, that is 23%. These are the overall results of the model, and we can see the specificity has increased manifold. Now to conclude the paper, there are several studies that has already conducted Parkinson disease diagnosis using voice signals. Feature selection techniques are used to reduce the dimensionality of the data set and improve the overall system of the performance, not only accuracy. So our aim was to use the two-stage feature selection technique in order to reduce the dimensionality of the data set and to improve the overall performance of the system. So the two-stage feature selection technique is able to increase the specificity to a great extent. So our accuracy is increased from 87 to 88%, which is not much, but specificity is increased to 52 to 70%, which is a great. Now, what is the future scope? There is a problem here of the class imbalance problem. That is, Parkinson patients are very less and healthy control are more. So we'll try to reduce this problem without using of oversampling and undersampling technique, as because they both have their own problems. In oversampling, there is increase in the redundancy, and in undersampling, there is a decrease of the sampling rate. Next future scope can be to test this technique on a larger data set to see the prominence of the results. And the potential of future can be employed to further check the diagnosis system. These are the references. Any questions?
Very nice. Like, what simulation tool you use for the purpose?
I have used Python
Python.
for coding. Yes.
Okay, fine. You've taken 5 parameters for the study.
Yes.
5 parameters. So why only 5 parameters? Like, what was the reason behind that?
Initially, most of the papers they use accuracy as a measure, but accuracy alone is not sufficient. Sensitivity and specificity are taken because they gives the accuracy rate of detection of Parkinson disease as well as healthy control. Similarly, F1 score is taken because it takes a harmonic mean and not a simple mean. Harmonic mean better tells the result as compared to taking simple
Fine. Are there any other parameters also available? They are not of so much importance.
Yes, we can take like true positive, false positives. We can take that also. We can take a confusion metric also.
Okay, fine. Thank you so much.
Okay.
Here's the next.
Yeah. Thank you, Ginny. And thank you, Rathore, sir. So we move ahead with our next presentation. So next presentation will be given by Sri Vidya. and Civil present a paper on IoT fog enabled framework for forest fire management system. Yes, this one is the second last presentation. After this, there will be presentation by Ross Arnold. Yes, Ridya, you can start.
Yeah, have a good day, everyone. Am I audible?
Yes, audible.
Yes.
Audible, please.
Yeah, my screen is visible for everyone.
Yes.
Yes, yes.
Okay. Okay. So today for this presentation, I have taken the domain of IoT fog-based enabled framework for forest fire management systems. So my application taken for this presentation is related to forest fires. The word forest fire we are hearing here from all over the countries during the reasons of the high temperature seasons. So this framework, what we are going to build will be helpful for the management people, those who are working under the forest survey to control the forest fires or to give notification for the people around the forest areas. So my agenda for today's presentation is introduction, then the surveys related to the forest fire frameworks already available, and the IoT fog-based framework, how this will be helpful for the forest fire management system, that is a proposed work, and conclusions and future works related to the framework and references. So I am from India, so I have taken the data related to the Indian forest fire. So during the high temperature seasons, as per the 2018 Forest Survey of India, there were 37,000 fires were identified. Here we are taking the MODIS data, that is called as moderate resolution imaging spectroradiometer data taken from the satellite. That will be helpful for identifying the data related to the fires occurred in the past years. So based on this data, 54% of occasional fires were happened and recurrent fires were 7%, and most of the fires related to high level were 2%. So half of the percent, that is more than 50% of the areas related to the forest fires were there. So this proposed work, what we are going to propose the framework, will helpful for to reduce the forest fire, and this will helpful for predicting the fires. The framework will help for identifying fires and give notifications for the users. So my literature survey is related to the basic wireless sensor networks, how they have framed the forest fire monitoring systems, then how IoT comes into the picture, and what is the role of fog layer in terms of forest fire detection systems. So the paper related to the 2016 forest monitoring and wildland early fire detection. So based on these normal sensor networks, they have taken different nodes to identify in remote locations. They gather the data of temperature, humidity, and seasonal parameters of the forest by using the sensors, and that will be taken to that will be forwarded to the communicator to the base station. So from these parameters collected from the sensors, they will identify that if there was a fire, they will give notifications. The major drawback of this one is due to the bandwidth and latency that was happened in the normal sensor networks. So we need some network that has to prefer for the lower bandwidth and lower latency, because we are working under the remote areas in the forest. The second literature survey related to the improved forest fire alerting system. So they have framed a middleware based application. So they will identify the locations of forest in the network where fire occurred. So this won't give, based on the data, once it is occurred, it will give alerting. It won't give any prediction.
Excuse me.
Yeah, sir.
Considering the time limitations, you can just come on your main framework, IoT framework.
Okay, okay, sir.
Literature review we can skip. Yeah.
Yeah, okay, sir. So our framework is related to IoT fog-based layers. So we have divided the framework in terms of 4 layers. The first layer only for sensing the data. So the sensors what we are going to deploy here having the low powers. So the working capability of these sensors only for sensing the parameters related to the environmental factors. You can take carbon dioxide level or humidity level or temperature level. So these sensors will be initialized here in the IoT sensing layer. Then all the data are collected to the aggregator level, where we are going to initialize the sensor nodes. That is, a node or router will have the more power when compared with the sensing data. So here aggregation is based upon the data. what type of data will be coming from the sensing layer. We are
Yeah,
aggregating here.
you have improved some architecture, or it is your own created architecture?
This is a created architecture, sir.
Before that, there was no architecture like that?
Yeah, we have the architectures, but the operations in the architectures may vary. The functionalities
Okay.
I have taken here in the fog layer is related to identifying the weather index value.
So this type of architecture is, I think, first of all, you are introducing. You want to say that?
Yeah, we have taken the architecture that based on that reference, I have modified the operations of the fog layer here.
Fine. So can you justify what type of operations you are modifying here? Like in all these blocks, what are the blocks created by you only?
Yeah, in the third layer, that is a fog or edge node. So that edge router is having more parameter, that is more capability in terms of power. So based on the real-time data, we are gathering the data in the edge layer that will do operations related to the fast identification of the fire weather value. So we are calculating the fire weather index. That is a general index that framework has been already there by the Canadian system. They are using this fire weather index that is called as WFWI. They are calculating this index to identify whether the fire will happen or not based on the parameters. So
how
we are
this IoT comes into the picture? How this IoT comes into the picture? Do you put some IoT sensor somewhere in the forest?
Sir, I have done the work based on the simulation level, not on the real-time basis.
But in real time, what will happen? Like, have you simulated
in
that?
real time, we need to place the edge routers or fog routers where we are going to place the operations of calculating the weather index value.
Fine. Okay, go ahead.
So all the data related to the fire weather index will be analyzed during the edge layer node that is having the more capability of doing the functionalities. So those data based on the fire weather index, the cloud layer, that is the topmost layer, will do only for alerting the people, those who are surrounding it. So we are not forcing all the power to the cloud layer. The edge routers that is nearer to the forest area will do the operations of calculating the index value. So this is the proposed work. We have done 4 layers: sensing, aggregator layer. And for this communication, for IoT based, we have used RPL based protocols and 6-LoWPAN based network communication. So to improve this layer, to improve the framework, we have an idea of going for the future work related to the protocol for architecture, how to do modifications or improvements in the RPL based protocol, that is routing protocol for low power sensor nodes that is going to be inbuilt in the forest area. So that is the idea, and the optimization of the fog node or router node. So these are my future works going to be carried on in future.
Great.
Yeah, that's it, sir.
Okay, fine. Thank you. Me, sir, we can call next one.
Yes. Thanks a lot, Srividya. So if anyone has any query or any question with Srividya, you can ask in the chat. Chat is open for everyone. So now we are moving ahead towards our last presentation. So it will be by Ross, and he will present a paper on multi-role UAV swarm behaviors for wide area search using emergent intelligence. Yes, Ross, you can set your presentation.
Okay. Thank you.
Yeah.
Screen here. Okay. Can everybody see that?
Yes.
Yeah, we can see. We can see. US Army.
Okay. Is that looks good?
Yes, it looks good.
Great. Okay. So I thought I had 12 minutes here. So since I have 8, I'm going to have to go through some of this material a little more quickly. So my name's Ross Arnold. I work for the US DoD, Department of Defense. I've been in the DoD for about 18 years. My background's mostly in software engineering, but I've also done some systems engineering research. And so today I'm going to talk about some swarm behaviors that we've been doing. It started as the cooperative program between the United States DoD and the Japan Ministry of Defense, and then it merged in with some other research we've had in the DoD. So I'm going to talk about a little bit about that here. So just briefly, the problem. So the problem is after a natural disaster, like we're talking tsunami or a major earthquake or a hurricane, really the first 18 to 24 hours are the most critical time to find survivors. But the problem is that this is also the most difficult time to search. So you have flooding, fires, and a lot of destruction. It can be very difficult for rescue vehicles to deploy and rescue the survivors. And actually, although I say 18 to 24 hours, it's really within the first 18 hours, and the earlier the better within that. So this is just a known problem in the search and rescue field, and it's been a problem for a long time. So what we were looking at is whether we can use some modern technology in the form of swarm robotics to try to address this problem. So just briefly on swarms. So when I say a swarm in terms of robotics, I'm talking about a group of robots, in this case UAVs, that are using cooperative behavior. And a group can be as few as 3, could maybe even just be 2, as long as they're cooperating. This doesn't have to be hundreds or thousands. It could be, it just doesn't have to be. The idea is that you have a group of agents that are working cooperatively and they're autonomous, or perhaps they're controlled by a single either person or a single computer. So what's going on when swarms are using cooperative behavior? In terms of our research, they're leveraging this concept of emergent intelligence. So the difference between explicit and emergent intelligence is here. So the idea is between explicit intelligence is sort of the intuitive method of intelligence that you would imagine from a human point of view. So you have a brain, and the brain decides what behaviors to do. That's kind of what we think about when we think intelligence. As opposed to emergent intelligence, this is a bottom-up approach where the behaviors themselves are what emerges, what results in the intelligence. So there's no central brain, it's just behaviors. So it's like much more simple, if you can imagine insects or some kind of very low intelligent creatures, where they actually behave in a way that is useful, but there's no one making decisions for them. So our swarm uses this concept of emergent intelligence, which has a lot of implications for system reliability and the ability to expand the system. So cooperative behavior, when I'm talking cooperative behavior, what I'm saying is essentially we have entities that are working together towards a goal, a common goal. They may not even know that they're working towards a common goal. And it doesn't have to require communication, may not be intentional. So just like we can see there, sometimes termites in the bottom pictures there can create these incredible structures that look like they were intelligently designed, but they're not. This is just a swarm of ants literally following their instincts. You can get a flock of birds. You can see the photo in the bottom left there that almost looks like it's some kind of intelligent design, but it's not. It's just simple behaviors of birds when they flock together. So this is the concept of cooperative behavior. So we're using cooperative behavior with emergent intelligence on swarms of robots to achieve our goals. So to do this, rather than implementing the actual system to start, I designed a simulator called the Drone Lab. And this simulator is, so it's specifically designed for emergent AI research with swarms. So essentially what you can do is just a Java program, and you can write separate behaviors for each entity in the swarm, and you can assign behaviors as a prioritized set, maybe 10, 12 behaviors like launching, avoiding, pattern searching, maintaining distance from each other. And the combination of those behaviors is going to result in a systemic effect. And so we can use that, try to leverage that with these realistic scenarios. And so we can fly a swarm of 20 drones over a disaster area once we acquire the survey data and see how it works. And it's a non-deterministic behavior, right? So we can try the swarm a lot of different times and see which configurations work the best. So that's the framework that we used for this research. And so as I mentioned, this was based on research that I had originally done in Japan. I was assigned there for 2 years back in 2016 to 2018, where we originally used the swarm for disaster search and rescue. And now we've been expanding it in the US DoD. So the original swarm used this concept of a social searcher or a spiral. All the drones were the spiral drone. And now we've expanded this to be multiple roles. So now we have an anti-social searcher and a relay. And these 3 roles we distribute the swarm based on these three roles to try to optimize the result. And so the picture on the bottom right there, you can see the drones. That red dot is essentially what is a survivor that's been located. So a standard behavior, a drone locates a survivor, and upon locating the survivor, spirals outward from that location. And this is because I discovered,
sorry, Ross, but actually your still slide is first. So can you please make the change?
I've been moving it forward.
Yes, perfect. Now it is perfect. Yes.
Okay, I'll just leave it like
you.
this then.
Yeah.
Okay. Sure. Okay. So right. So that red dot in, can you see my mouse there too? Is a survivor. So the spiral drone will locate that survivor and spiral outward from that location, and then continue on its path. The antisocial searcher will maintain a certain distance, longer distance from other drones than the social searcher, which maintains a kind of a tighter swarm configuration. And then we have this idea of a relay drone, and this maintains a distance of about 400 meters from the center of this, from the its closest neighbor, which is the idea is it can relay Wi-Fi signal, so we can expand the swarm and still be within Wi-Fi range. So this is what we use, these three different behaviors, distributions of 10 to 50 drones, and we distribute them according to this method called the design analysis of computing experiments. So what we did was took all of the distributions of those three roles of sizes between 10 and 50, so 10, 11, 12, and determined the optimal 100 configurations, which would give us the most statistically likely result. And then we did 10 repetitions of each of those, so 1,000 runs, and then compared those results. That was the experiment we did. So what we found was actually the optimal configurations. They highly outperformed our prior research. So we were able to locate 90% of survivors in 25 minutes. Previously, we got to about 45 minutes with our optimal configuration. So we almost cut that time in half. And as you might imagine, the more drones in the swarm, the more rescue missions per hour. But there is a point at which the swarm doesn't have to necessarily be 50 assets in order to achieve a good result. Like we can use maybe 35 or 40, and we still get a very good result. We even had some results with lower swarm sizes, like 25, which were almost as good as the larger swarms. So that was very interesting to see that. And we also noticed that the distribution of relay drones kind of vastly affected the system, more so than our spiral and antisocial roles. And that probably is because as the relays are not actually actively searching, they're maintaining a distance between other drones, and therefore they don't search as effectively. So some additional observations we had. So on the bottom left, you can see the spiral drone proportions seem to be constant throughout all of our runs at about 18 to 20% of drones. So we don't know if that actually generalizes to different scenarios or not, but that was very interesting to see that no matter what number of drones we did or what distribution of roles, we always wanted 20% of those to be the spiral drones. So we're trying some different experiments to see how that generalizes different scenarios, like different sets of terrain, and see if that assumption holds true. And then on the bottom right there, I showed the graph of the 30 drone swarm. You can see the greens and blues of the spiral, just indicating that essentially that is not the critical number of drones for the swarm. It's really more based on the relay and antisocial numbers of relay and antisocial drones. So one of the things we're really looking for here is, can we find a configuration of these roles that is smaller, that actually works very well, on par with a larger swarm. So some of the future work that we're doing here, what we're trying to do is generalize this to a couple different scenarios, so urban and rural. And so can we find configurations that generalize to lots of different terrain sets? And as I mentioned, what smaller swarm sizes are performing on par with larger sizes? And actually one of the key pieces of our work is this concept of design and analysis of swarm computing experiments, those DASC methodologies. This is a brand new method. And so it goes beyond just our specific results and the method that we're using to achieve those results. And so far, in terms of swarm computing experiments, there doesn't seem to be any kind of generalized framework for this. So we're trying to develop this framework or methodology that we can share, with the rest of the world, so that everyone can have a basis, a statistical basis from which to launch swarm experiments that actually works well. And we're also expanding research to other mission areas, looking for landmines, unexploded ordnance, combat search and rescue, things like that. So in a couple of different directions, we're taking the research. So that's all I had. I try to keep it to 8 minutes there. Just have my references, resources, and we can move on to any questions.
Yes, thanks a lot, Ross. Yes, Professor Vijay, do you have any question?
It was good, but in your own observation, what are the limitations of this your research?
The limitation. Well, so firstly, we
Like,
ran
what would you
swarm.
like to improve?
Yeah. So we ran the swarm. It's on a specific. So the original experiment is on a specific town in Japan that was hit by the tsunami in 2011. And I actually went there and looked at all the building locations and talked to the people there and got the data. So I have very specific research data from that town. So that is correct. I know where people were rescued from, and I used that to design the environment. But I don't know if those results generalize to other scenarios. So definitely a limitation is we don't know how well the same configurations are going to work, given maybe buildings are in a different location, more people are in different places. That could change a lot depending on the different scenarios. So we really need to, we need to expand it to different scenarios.
Yes, thanks a lot, Ross.
Thank you.
Yes. So now we move towards the ending of the session. Just in a minute, if you want something to say, Dr. Rathod.
I would like to appreciate all the papers. It was very nice and knowledgeable. All have done very nice efforts to present the papers. And I wish you all the best and you improve your work. And next time, let's hope to meet one-on-one in London again. So I congratulate you and your team for organizing such a nice conference. And thanks for providing the platform to discuss these ideas among each other. Thank you so much.
Okay, thank you, Dr. Vijay. Now, thank you, everyone. There are just few things that I would like to tell. Like everyone might you have received a copyright from the IEEE, or you will receive within a day. So please complete that as soon as possible, so it goes into the next phase. Now you will receive few things from our side within an hour. One is your presentation certificate. Second, contribution certificate, one thank you letter from our end, and your payment receipt. If you have any query, any changes in the name, in the receipt or the certificate, you can just reply to that mail. So the team will update in that, and it will again send back to you. Now, I really wish all the success to everyone, and really I will hope to see you again in the next year in person.
For sure.
Yes, in person in the London.
Next time, see you all at London.
Yes, next time with you all at London. If from your end you need any help, just write to us. Thank you. Thanks a lot, everyone.
All the best.
Yes, thank you. Bye bye.